So in computer graphics, at least that was not attendance. So for people wondering, that was not attendance on the blocky world. There'll be an attendance survey. We'll get to it in, I don't know, 20 more slides, something like that. So what's lighting for in graphics? Well, lighting in movies, in graphics, in games often sets the mood. So far, we've had no lighting. We've just had textures. And we've seen that people have been able to fake a little lighting. In fact, even just a little bit of blending with a black texture was able to fool me. But we could have spotlights. We could have dramatic lighting on faces. There's a variety of different things that we could have. Indeed, if you go look at photographers, you know, they have whole books and sheets about how should you get your lighting right so that you make your photography look good. So of course this applies for movies. It also applies in graphics. If we think about examples like this picture, so this is a picture inside of a slot cave. It's all sandstone. It's all brownish. There's not much color difference, but we see a color difference. This is almost black. This is almost white back here. Why? Because of the lighting on the surface. And so this is what we want to be able to capture. So from today's lecture, we hope to be able to add this to our world, where given the same color block, we can see something about the shape of the world. You have a pretty good idea of what the shape of this slot canyon looks like, even though it's all the same color because of the shading on the surfaces. Our human visual system is really good at figuring out what's going on with reflectance and lighting. So if I ask you which of these spheres have the same material, I'm sure you can all identify that the A spheres are similar and the B spheres are similar and the C spheres are similar and the D spheres are similar, in the sense that this is kind of diffuse like a ping pong ball, and this is black like the 8-ball in pool, this kind of thing. This is chrome. But if you look at the raw pixels that are being generated, the relationship is the other way, right? If you consider this picture and this picture, it kind of has a white spot up here and then kind of grayish below, and this one has white spot up here and grayish below. So if you did mean square error or something to calculate the difference between these pictures, actually the top row is more similar and the bottom row is more self-similar, but we don't perceive it that way. We perceive by the material. So our goal is going to be to create some simple mathematics that will let us make different kinds of materials. So let's look at the simple reflection of light off of a surface. So if we just have a metal surface, a light ray comes in, and if it was a perfect mirror, the light ray bounces off in a reflective direction. And if we have something transparent, the light ray comes in, some of it bounces off in a reflection, some of it transmits through the surface. Real surfaces are not these perfect mirrors. So real surfaces have this little it's called microgeometry in it. And when the light ray comes in, actually it's like some little interaction happens here on the surface in the physics, and light bounces out in multiple directions, not just the mirror direction. So these scissor blades are meant to be a representation of that. And what these arrows out mean is what fraction of the light is going in which direction. So the largest fraction goes in our reflection direction, but some goes in some other directions. Chalk has something called subsurface scattering. It means the light goes into the surface, actually bounces around in the surface, and comes out maybe in a different location and in all kinds of different directions. So we're going to draw some diagrams that are going to look like these to approximate what's going on with our light. So these are the ideal lighting that we talked about, right? Here's an ideal reflection. Here's a transmission. If we have a rough specular, this is what we're going to call specular in the model that we're going to build up today. The light comes in, and this is the same as the picture we saw before, except for with the arrows removed. So let me go back. Here's our picture before. We have arrows, and how much light is going in each direction is making this kind of ellipse thing, right? So here's the ellipse. For each angle, we can read off what fraction of the light goes in that direction. So Lambertian, also called diffuse, is a special case. The light comes in, and it equally bounces in all directions. It doesn't really care about the orientation of the surface. In this case, we cared about the orientation of the surface. So what do these things look like in computer graphics? So here's Lambertian or diffuse. All the light's all going in the same directions. The same amount of light reflects in all directions off of the surface. So here's some renderings. So this is a flat or diffuse looking kind of object. So what does it look like if I have this more specular kind of look, where the light is bouncing off in some specular lobe? Okay, now we can get more metallic or plastic. Importantly, we have these highlight kinds of things going on in our surface.